The next speaker is Victor. Okay, so let's welcome the speaker.
Thank you. Thank you, everyone. So I'm going to tell you today about the work that we've been doing on trying to interpret through DFT calculations the ARPES data in this intercalated two-dimensional materials. So what we do is we do DFT calculations based on these codes that I'm showing there. All the electron structure calculations that I will show were carried out using the V2K code. And also we'll present some phonon calculations that were obtained using the VASP code and the PhonoPy. Those were obtained by my former PhD student, Jan Phillips, who is now a postdoc at INL in Braga. And these results I'm showing is part of a much broader project that I have in collaboration with Santiago Blanco Canosa at the North International Physics Center, trying to understand interesting properties of two-dimensional materials. So, okay, this is the material that I will tell you about today. So it's an intercalated compound where you introduce either cobalt or iron in the 2H tantalum S2 structure. You see there that we have a laser pointer. Well, I don't see it. I will try to use it here. So you see here no, it's okay. It's better in the screen, so it's recorded. So you see here this transition metal sits in the van der Waals gap, and it's surrounded by an ion octahedron. So this will be important to understand the electron structure. And the fact that we have a 1/3 stoichiometry means that you need to enlarge your unit cell by square root 3 in the plane. Okay, so our colleagues took some magnetization data of these two materials. This is just reproducing what was known in the literature. In particular, the cobalt compound is really complicated, as we saw in talks before. What I want to say here is that for my calculations, I stuck to antiferromagnetic collinear orders, and let's see if we can understand with that the basic features that are seen in the ARPES. So this is the basic, let's say, density of states, cartoonish of this compound. We will have up here the tantalum D bands, down there the sulfur P bands, and in the middle, somewhere there, we will see the metallic D bands. So the first thing that I want to emphasize is that, well, this will be really mixed up. It's a metal system. All the bands will be really hybridized. So it is difficult to actually say what ionic state these metal atoms will have. Okay, so there will be somewhere between 0+ and 3+, and that would mean that probably the tantalum D bands get somewhat occupied, and that's difficult to quantify. Okay, so for the cobalt compound, these are the density of states. This is for one of the cobalt atoms in the system. This will be a spin up, and down here will be a spin down. We see that the cobalt atoms have a moment. All the cobalt majority states are occupied, as you see in this cartoon here. The T2G and EG states are split like that because of the octahedral crystal field around cobalt, and the tantalum D bands are mostly up here. And yeah, the electron count for the cobalt, one can think of it as somewhere in between D8 and D7, as you see from this density of states here. If you look at the bands, these are the GGA bands here, and try to extract a Fermi surface from them, we see that we have some hole pockets here around gamma. These are in the Fermi surface, these ones here. But if you compare with the experiments that our colleagues took, it doesn't fit. We see additional features here at K that are missing in this calculation. So what we said is, okay, probably we don't have a excellent control of how much cobalt we have in the system. So what happens if we lower the chemical potential? If you do that, if you lower the chemical potential, you can create an extra pocket here and an electron pocket down here. And we will see that this fits much better the Fermi surface that is obtained experimentally. Of course, you can quantify what you have just done. You can count how many electrons you've shifted in the system. So to obtain this particular band structure here, what you would need would be something like cobalt 0.3. Of course, this is just a naive estimation by the number of electrons that I just shifted, okay? But if you do that, you end up having this Fermi surface here, which matches pretty well what is observed experimentally. So this Fermi surface that that our colleagues measured mimics quite well what is observed in typical Kagome materials. So this opens the door for you to actually design with these intercalated materials, for example, a Kagome-like Fermi surface. So you can compare a bit further the ARPES data with your calculations, and you can see that these pockets here that are around K basically come from the cobalt D and tantalum D hybridized bands, and that these pockets around gamma, the circular ones that we saw in the Fermi surface, also come from tantalum D and cobalt D. So this additional band that we call beta prime is the one that is mainly tantalum D. Okay, so what happens if we have iron? So the first thing that we notice in our calculations is that if you do a standard GGA calculation or LDA calculation, the iron moment is in a low spin state. And when you introduce a U in the calculation, if you do LDA plus U calculations, your moment increases like this. And what we see in experiments where our colleagues measure is that the iron is in a high spin state. So we used LDA plus U calculations with this value of U to try to mimic what they were observing. This is how the density of state looks like in that high spin state with LDA plus U. And you see that, again, the iron D states are completely full, as in this cartoon here. And the number of minority iron D states that are below the Fermi level is around, well, something like 2, something like that. It's again, it's a non-ionic system, it's a metal, so ascribing a particular valent state to iron is basically, it's not that useful. The main difference between the iron and the cobalt compound is, of course, the fact that cobalt is smaller. The cobalt D bands are lower in energy than the iron D bands, and this creates this change in the electronic structure, that the tantalum D bands up here in black come much closer to the Fermi level in the iron case. So in the iron case, you will have a much stronger hybridization between tantalum D and iron D states. Okay, let's look at the band structures that we obtained and try to compare them with our colleagues' ARPES data. So if you again take your band structure and try to as out of the calculation and try to compare it with ARPES, nothing matches. You have this flat band here around gamma that is missing in the ARPES data. So again, we said, okay, what happens if we shift down the chemical potential, if we reduce the number of electrons in our system just by a rigid band shift? If we do that, this band can come up from the Fermi level, so it will not be seen in the ARPES, and we will get this extra pocket here at K, this additional electron pocket here together with these whole pockets at gamma. And so if you look at the calculated Fermi surface up here compared with the experimental one, we see that they match each other quite nicely. You have these circular pockets in the zone center, and at the K point you have these features which are more or less what is observed in experiments. In this case, we needed to shift the chemical potential substantially so that the nominal electron count, just by counting how many electrons we remove from the system, would give you something like iron 0.27. But this is only considering that the change would affect only the iron atoms. Okay, again, looking in detail at the band character clocks to the Fermi level, you can see that your states that give you these pockets around gamma come from both tantalum D and iron D. In this case, you see that because the hybridization between tantalum and iron is much stronger than in the case of cobalt, you have components from both atoms in all the bands involved in the Fermi surface. Okay, so our colleagues had additional data that I will not have time to discuss in detail, but this is an X-ray diffraction diffuse scattering data. So the brighter spots are Bragg peaks, but apart from the Bragg peaks, what they see are additional diffuse signal. So that often means some kind of short-range order correlations in the system. So usually in these two-dimensional materials, those are correlated with things like charge density waves. So we thought maybe that was the case, and we calculated phonon spectra to see if this square root 3 times square root 3 structure was unstable to some kind of distortion. And we did it with and without magnetism for the cobalt and the iron case, and all structures are dynamically stable, so there's no indication in our calculations that any charge density waves may occur in this system. And also we did it for this compound, and this compound at low temperatures, it does undergo a charge order transition. But as we see, that transition is not driven by anything that you can see in the phonon spectra. The phonon spectra are all of them dynamically stable. So what is driving that transition has to be of a slightly different origin. Okay, so these are all the people that were involved in the project. I only had time to discuss what we did in this, which is the DFT calculations. So the ARPES and diffuse scattering measurement were done by Santi Blanco Canosa. The resonance scattering data, which I didn't show, was done the UC San Diego team. Samples came from Berkeley, and they did all their measurements in all of these facilities all around the world. So this, you can find more details about our work in the archive, and these are the main messages that, you know, with these collinear DFT calculations, you can give an understanding to the Fermi surfaces. With these intercalated compounds, you can engineer a Kagome type Fermi surfaces, and you can describe what the origin of the different bands is. And also, our phonon data showed that there are no predicted reconstructions in the form of charge density wave in this material. So that diffuse scattering data you see has to have a slightly different origin. So with this, I thank you for your attention.
Thank you. So any